we've got over 155 people who've registered, so quite a few of you guys there. We're muting everybody, but we are going to take questions, but not verbally. So via the chat within Teams, you can put your questions in at any time. My colleague Mike Kenny will get on and answer those as we go through at the end of the meeting. We may not get through them all, so don't worry, we will answer them separately via email or other medium. So we will get all of your questions answered, and don't worry that they may be silly questions. We're happy to help you with your flow chemistry questions there. Today we are Asynt, so we are a company that specialises in products for chemists, novel products, benchtop tools, and for some time now we've worked really closely with the University of Leeds, with Professor John Blacker and Nick Kapur, and they're going to be presenting the science and the chemistry behind fReactor today. But they're also very keen to work as collaboratively as possible with more academics and more industrial organisations. So if you like what you hear and would like to find out more about maybe potentially collaborating with Nick and John, then you'd be able to drop them a line at the later date. What I'm going to do, I'm not going to tell you any more about Nick and John. I'll let them introduce themselves and their department. We're going to start with Nick, and he'll be running you through the sort of the hardware side of fReactor, the physical properties of how it works, and then John will go on to more of the chemistry science afterwards. And then we'll take the questions via my colleague Mike. So with that, I'll hand over to Nick.
Thanks, Martin. Excellent. So thanks very much to Asynt for hosting this webinar. Myself and John will introduce ourselves in a moment, but before we go into PowerPoint, I just thought I'd show you what a typical fReactor is. So this is a single stage of 5 that normally sit together. It's very easy to use. Okay, and I just want to show you how easy it is to use before we go into the video. So there's a thumb screw on the front. If you take that off, you can get into the inside of the fReactor. So there's a glass window, and then there's a little magnetic stirrer. And reassembly is just the opposite process. So if you need to get in and clean these things out, or after you've finished your reaction, you can do that. And just reverse that. So very, very quick and easy to assemble and disassemble. They're rated to tens of bars of pressure. I think we say about 7 bar is safe, but obviously there's an upper limit above that. And it's got ports on the side of this. So this is just set up with 1 input and 1 output. And there are 2 stopper ports in here. But again, it's very easy just to take these out. There's another pipe there. So that's now got 2 inputs and 1 output, or 1 output. And then you can put instrumentation in. So if I take this port out, this is just a thermocouple, standard thermocouple going through a standard HPLC fitting, and that can screw in the side so you can measure temperature. So that's the single units that we'll be talking about, and I'll show you how those fit together. So I'll show you that now before I go into now PowerPoint. So let me just share my screen. So as Martin said, we're talking about flow chemistry in general today and talking about what we've been doing with the fReactors. So I'm Professor Nick Kapur. There we go. I hold a chair in applied fluid mechanics and a degree in chemical engineering. I'm based in the School of Mechanical Engineering at the University of Leeds. And my interest really is in the fundamentals of fluid flow in many different situations. And I work very closely with industry as well as many other groups in academia in realizing flow concepts. And I've been particularly working with John and with an IPRD for about 5 years now, where we've been designing different types of flow reactors to enable different types of chemistries. John, do you want to introduce yourself briefly?
So, hello everyone, I'm John Blacker. I'm Professor in Process Chemistry, University of Leeds, Director of the Institute of Process Research and Development, which is dedicated to developing new research and development methods in process development and manufacturing. And my particular expertise is around route design and chemical process research and development, including a lot of flow chemistry, as we're going to talk about today. So,
thanks, John.
Nick.
So John mentioned IPRD. So IPRD is our Institute of Process Research and Development. And it's within IPRD that we've done many of the developments of the fReactor. This was never a big funded project externally. It was something that we started. And the students within IPRD, they're a mixture of engineers and chemists and biology students, and the academics have all got involved in this project. And it's really, IPRD is, has a physical base. It's got really great laboratory facilities for doing small scale through to large scale synthesis of chemicals. And around that is a whole group of academics working in different areas. So it's a really great place for students to work and postdocs to work and for research to happen, because there's this very interdisciplinary research environment. So that's sort of where they've come from within the University of Leeds. So what I'm going to try and get over to you today is what we've been doing a little bit around flow chemistry and more about the fReactors themselves. So the single fReactor unit that I showed you is a single continuous stir tank reactor. And you can see two of these down at the bottom of the screen. So this is our standard size fReactor. It's got a volume of about 1.8 milliliters, and this has a volume roughly of about 8 milliliters. So this is a bigger scale unit that we're just launching, and they sit on a stir or hot plate here. We've celebrated this one with balloons, and you can flow in and around those, and I'll be showing you that in a moment. What I want to get over to you today in my part of the talk is how and why we use them, and some examples of chemistry, and John will be talking quite a lot about different examples of chemistry. So I thought I'd start with a video, and this is a video of reactors in operation, and what we have within this is it's a physical process really. So we're mixing oil together with water and a green dye that we've put in the water phase, and you can see just how easy and straightforward these are to use. So this is the fReactor unit on the hot plate. So there's 5 of these together, and I'll mention why in a moment. And we've got a dual feed into the first fReactor. So that's our first fReactor. And you can see here in this syringe, we've got our lovely green water, and in the bottom syringe, we've got our oil. And these are sat on a dual syringe pump. So that's a pump that pushes the syringes in at the same rate. So we've got a 1-to-1 ratio. And there's a stirrer hot plate within this, and that's going to provide the stirring action. So there's a magnetic stirrer in each of these. And you can see fluids coming in over on the left-hand side, and it's flowing its way around through these 5 stages. And you can see, if I just pause that there, you might be able to see, if your contrast is good enough, you've got this very fine emulsion of material leaving after the last stage. Okay, so that's a very typical physical operation. There's no real chemistry taking place, but it gives you a feel for what's going on. Now, this is a slowed down video of actually what those stirrers are doing. They're actually bouncing around within the reactors and giving really good mixing. Now, I just want to contrast that with the other type of reactor that people often use for flow chemistry, and that's a tubular reactor. And what you'll do is you take a tube and a T-piece, and as you'll see, you bring oil and water together. So there's our water phase and there's our oil phase, and that mixes within the T-piece and then flows out. Now, although it looks really pretty, you've got this very, very regular drops of water within the oil phase. So we've got an oil continuous phase. You've actually got very small amounts of surface area for any mass transfer between those 2 phases. So the mixing in this type of systems nothing like the mixing that we see within the fReactor system. So this is an example of a multiphasic type reaction. So that's quite quick, but you'll see I've broken out some of the slides in a moment. So just from a physical perspective, what we have on the left-hand side here is our dual syringe pump. So you have a choice of how you want to pump, and the way we've tried to design the fReactor is to make it as flexible for people as it can be, okay, without becoming too difficult. So to use a fReactor unit, this is the fReactor shown in the dotted circle, you attach a pump. So we're using a dual syringe pump. We often use single syringe pumps, and then you can control the ratio of the flows independently. Syringe pumps actually are very convenient, particularly if you've just got, say, an aqueous phase and an organic phase. You can also suspend solids in them, but you have to make sure that you don't separate your solids out in your syringe. So sometimes we sneak an extra stir a hot plate under here, and we put a magnetic flea in there. So there's tricks like that you can play. You can use peristaltic pumps, but the pressures you might achieve might not be quite as high as within a syringe pump. Sometimes you use HPLC pumps, gear pumps, and diaphragm pumps. So there's a kind of a choice really around pumping, but actually syringe pumps with an appropriately selected syringe, so the materials have to be compatible with what you're using, actually are very convenient as a starting point, and that's often where we start. So things that you might consider when you're choosing your pump are the maximum pressure you want to generate, whether you've got solids in there, material compatibility, and then general flexibility. And really that's it. So you take your pump, you stir a hot plate, and many of us have stir hot plates in our labs already, and you add on a fReactor kit. And with a bit of chemistry, you become a flow chemist. It's nothing more complicated than that. And I think sometimes we build these things up in our minds, and actually it's really easy technology to access. Now, when we're operating flow chemistry equipment, we tend to go through different phases of the process. So the first phase is a startup phase. So typically, and in this example, I've started with the oil phase within the fReactors. So I would have turned this on, I would have flown oil through the reactors at a few milliliters per minute until I've pushed all of the air out of the system. Okay, and then I'm going to go into my, well, in this case, a physical transformation phase. So I would turn on my aqueous pump and I would turn on my oil pump, and you can see it takes a few minutes for our material to flow from the inlet to the outlet. So you can see, I think, probably just in these two reactors, it's starting to turn green, whereas these are still clear. So we have this startup phase where our materials are coming together for the first time. And if we were monitoring something like yield, what we would see is over time, our yield of our product would go up, and then it reaches a steady state phase. And we can run this for as long as we want. And that's one of the really nice things about flow chemistry is if you need more material, you leave your reactors running for a longer time, and you can generate material and scale up data in that phase. Okay, and then we have the shutdown phase. So maybe we turn off one of the two feeds and then our yield would start to drop. Or we could just turn off the reactor at that point and maybe empty the contents out. And typically, around 2 to 3 volumes of the whole reactor is the amount of material we have to flow through to reach that steady state phase. So roughly, this is about 10 milliliters of volume within this reactor. So typically 20 to 30 milliliters of flow goes through the reactor before we reach that steady state phase. Okay, so that's typically what we see within a flow chemistry situation, as opposed to a batch chemistry situation where we might bring our materials together and we don't change, we don't continue to add. In some cases you can do, but generally we bring our materials together at the start of the reaction, we stir them, and they change continuously with time until the end of the reaction's reached. So that's one of the differences between flow and batch chemistry. Now, within our reactors, and one of the reasons we designed reactors was because we were particularly interested in multiphasic chemistry. And John will give you some of the reasons about why we're interested in multiphasic chemistry. When But what we have within each reactor is we have an active mixing. So there's a mixer that bounces around within the fReactor, okay, and produces really good mixing between different phases of materials. So in our case, we've got two immiscible fluids, and this active movement maintains a high area of liquid-liquid interface. So if we're expecting chemicals to transport from one phase to another, maybe after a reaction or during a reaction, this is a really great way of maintaining this interface. We can suspend solids, so we can suspend catalysts, and we can actually crystallize within the reactors as well. And because we're continually moving material around, we find that the crystals tend to stay in or suspended in the solution. They do sometimes aggregate on the walls of the reactor, but generally not so badly. And actually, we've performed some really nice crystallizations within these. Now, ultimately, you might get a blockage, but then you've seen how easy it is to shut the reactors down to clean things out. And we've also done quite a lot of gas liquid mixing as well within the systems. And I'll give you some examples in a moment. Point the back on. So I suppose really the difference between the reactors is that we've got active mixing within each element, and there's a really good local energy input. We're adding energy into our system to keep those two phases mixed together, and that means we've got really good mass transfer between the two phases. Now, just by way of example then, I'll jump over to the right-hand side. This is a typical tubular reactor system. So this pipe might be wrapped around a mandrel that keeps it hot. We have much poor mass transfer really for these multiphasic systems. So you can see the interfaces between the green and the clear actually are not big areas per volume of fluid. Okay, so that means we've got diffusion control of these interfaces, and even with single phase chemistry, so maybe we have two miscible chemistries coming in over on the left hand side, then it's still diffusion controlled. Okay, so again, the mixing characteristics are very slow within these types of systems. So over on the left hand side then, reactors, just by way of an example then, so if we're running at 2 milliliters per minute, typical mid-range flow that we would be using for these, it gives us about a 4-minute residence time within the reactor classic. So that's how long it takes from, on average, from the inlet to the outlet. That's what we mean by residence time. And if we were doing that within a tubular reactor system, we would be using about 5 meters of an 1/8-inch diameter PFA tubing, and we would need a heating element around that as well. Okay. Here again. Right. So I just wanted to talk about the operating characteristics of the reactor and what these have really allowed us to unlock within IPRD. And what we're finding is that actually having these within the lab, people go to them without much prompting, they pick them up and they start to use them. They're very easy to use, okay? I mean, I showed you, if you can finger tight a fitting, then you can assemble a fReactor, and it's really that easy. So there's a very low barrier of entry to flow chemistry, but it's a very effective flow platform from a chemistry perspective. It's reusable and robust. I think say that there's a pressure limit of 100 psi, so a 7-bar pressure limit on those. So why that's important is because we know that to push our reaction rates, we generally want to go hotter with our reactions. And many of our solvents will boil before the temperatures we ideally want to reach. So by putting a back pressure regulator on the end, what you're doing is you're increasing the pressure within the system, and the boiling point of your solvents also goes up. So it allows you to access higher temperatures and faster rates. Okay, so that's why we tend to use back pressure regulators. And if we've got gases in there, so if we're doing gas liquid reactions, then by pressurizing the gas, we end up with a sort of a higher partial pressure. And that means there's a faster mass transfer from our gas phase into our liquid phase. So that's something about pressure. The materials of construction, if you need specific materials, you can talk to Asynt, but the kind of base unit is a peak reactor, so it's very robust to most chemistries. I think it doesn't like chlorines and bromines and things, but for most chemistries, it's very good. It's got a temperature rating, usable rating of about 140 degrees C, and then it just depends on the pipes and other bits and pieces that you're using. And you can use that with the standard hot plate, and it's easy, and you probably have one. So there's also been quite a lot of chemical engineering thought that goes into this. So you can see straight away we've got roughly exactly 5 and roughly 2 milliliters per reactor, so about 10 milliliters of volume. So doing this in 5 2 milliliter packets is better than doing it in 1 10 milliliter packets, okay, because of the residence time distribution. So we often talk about a mean residence time, but some fluid entering a reactor like this can go through very quickly, and some fluid can hang around, and that's what we mean by residence time. So some packets that go in spend a long time in there, some packets that go in spend less time in there. And the wider that residence time is a sort of means that you've got more variation within your reactor. And chemical engineering principles say if we've got smaller reactors and more of them, that's better than a larger reactor and a single one of them. And I'll talk about these links in a moment. And we find there's great flexibility within these reactors. I showed you how easy it is to add pipes in. Sometimes we feed into our first reactors only, sometimes we put other feeds in down the cascade, maybe to try and keep a particular reactant at high concentration. All of that's very flexible within our reactor system. Yeah. Fine. So one of the things that we've been trying to do with Asynt is we try and feed technology through so that as we develop pieces of kit within our laboratory, these become available through Asynt. You know, there's a product development cycle that we go through, and ultimately it gives you the same robust platforms to work on that we're working on, and with really good engineering principles. As you can see, they're really easy to use. So this is an example of a gas liquid reaction using some photochemistry. So this is tetralin to tetralone. So there's air in the system, so that's our carrying oxygen, and then there's a photochemical initiator within our system as well. Okay, so we developed a cascade of UV 365 LEDs within our labs, and you can see they're not, you know, that's not commercially viable yet. It's still quite laboratory based. Lots of advantages within CSTRs with photochemistry, because actually you've got this really active mixing, and you can maybe see that on the next slide. Because you've got active mixing, it's mixing light, mixing fluids up into the active region where the photon count's really high, and then back down again. And that's contrasted with photochemistry within the tubular system. So if you were doing a gas liquid reaction like we're doing here, and this is an example of what would happen, you would have slugs of gas, slugs of liquid, slugs of gas, and then your light intensity will be highest nearest the top of the tube. So there's really good advantages to doing photochemistry within CSTR systems, okay? And we found really good performance of our gas liquid systems in this example here. And if you need further information about these, feel free to contact us afterwards. And this is where we kind of at the moment. So we're working really closely with the Asynt to bring photochemistry modules out. So these are our, I don't know, beautiful yet, but they're performing really well. They've got 365 LEDs in them, and they sit on our standard reactor plate. So this kind of idea of modularity and allowing you access to broader chemistries, and also allowing you to choose what you want to do your chemistries, is a really nice concept that we're developing. I just wanted to show you two other things as well, really. So this was an example of a hydrogenation reaction, and we weren't actually using the fReactors for flow reactors, we were using them as batch reactors, okay? And the idea behind this was, because all of these fittings are really standard, you can kind of go to catalogs and choose what you want to buy. So here we've got a back pressure regulator, and this is a safety regulator within this system. Here we've got 2 ports blocked up. And here we've got a little valve that's a little bit like the valve on your bicycle. So you put this in to the fReactor, and what happens is you can pressurize with your syringe, and it pushes gas through the system, and then it's locked into that reactor. And by doing this multiple times, just like when you pump up a bicycle tire, you can essentially pump up your reactor to a particular pressure. And it's very easy to generate tens of bars of pressure using a system exactly like this. Okay. The nice thing about the fReactor system is you get 5 of these, so it's very easy to heat and run 5 screening reactions at once. And I think John might mention something about those. We also did some work where we were measuring the pressures within the reactors. So this is a standard pressure probe and an adapter, and there would be a pipe that went from there into our reactor. And from that, we were able to get some mass transfer characteristics. And actually we found, so this R number is the ratio of liquid, of gas to liquid. So we found for a particular R number and a particular rotational speed, we got really good mass transfer characteristics within our systems, okay? And shown over on the right-hand side is a PAR reactor that we have in our lab. I think it's a 2-litre PAR reactor, overhead stirred, much more traditional, larger volume reactor we would have used for hydrogenations. And you can see we're actually getting much better mass transfer characteristics than we would in the PAR reactor, but certainly of the same sort of size. So it's showing that you could use these for screening, for example. So you can pick off a reactor after 10 minutes, 20 minutes, 30 minutes, quench the reaction and see where you're at. And then this is just one last slide, really. This is a standard pH probe. We've also just worked with Asynt just to launch a new lid for the fReactor where you can take one of your standard 12mm probes. So it could be conductivity, it could be pH, whatever you want it to be. And that fits on in place of our normal lid onto the fReactor, and you can measure other things. I showed you an example with temperature, but now you could add pH, for instance. And like I said, we're developing new technologies all of the time, and we're always interested in passing these through. But in the interest of time, I'm not going to go through all of those. Last thing I just want to say is, myself and John are really passionate about getting people to use flow chemistry. It's one of the, the pillars of green chemistry, and we think it's really important. We have developed some educational content as well, because we realize people haven't necessarily done flow chemistry as undergraduates, as chemists. We're trying to change that within Leeds. Our undergraduates, when our labs are opening, do flow chemistry with John. But we've put some information on these web pages so you can find out about flow. There are some online modelers in there, so you can explore what happens if you have 3 reactors compared to 5, and what that means for residence time, and some of the technical language that I've used today that you might not be that familiar with. You'll find lots of information on those web pages. Okay, and I think that's about me done. So I'm going to stop sharing my screen and hand over to you, John, who's going to talk about chemistry.
Right, so following on from Nick then, I guess the first thing to say is, why do we want to do multi-phase continuous flow chemistry? And the reason is that when we're doing process development, most production processes, most processes involve gases, liquids, solids, and various combinations. And if you're using tubular reactors, there are definitely limits on having gases and solids in there. They work very well with liquids. And the reason is that we often exceed material solubilities in order to try and improve productivity. So we might feed in solids, or we might get solids produced within reactions, or we might generate crystals as we're going through. We might have solid catalysts and so on. Processes can often require or evolve a gas, and so again we can end up with multi-phase systems. We might want to do liquid-liquid reactions with 2 liquids in there, for example, during workup and extraction, things like that. Or we might want to do crystallization, where we generate crystals in flow as well. And as we're all taught as undergraduates, batch reactors work very well with that, because the flea, the round bottom, in a round bottom flask with magnetic stirrer, they cope very well with lots of different phases. And we never even think about the mixing really in there as chemists. And when we try to do reactions in tubular reactors, as people know, they perform very poorly with solids, and gases and liquids are even problematic as well, though there are ways around that, some of those. And what chemists tend to do is they tend to circumvent or avoid the problem by designing homogeneous liquid systems. So they dilute things down until everything's soluble, and then they can flow it through a tube. But the consequence of that is that you've got a system that's less productive. It limits the scope of the reaction because you might have things that are still not soluble when you dilute them down, and it can ignore separation and workup aspects as well. So that's why we wanted to work on multiphasic flow systems. And the fReactors was one way of doing that, as you've seen from Nick's presentation. So I'm going to tell you about some examples of the use of the fReactors. So I've got 6 examples here. First one, an undergraduate experiment that's very instructive and very easy to run. Second one is a bit more complicated. That's either a gas liquid solid system as a palladium carbon hydrogenation, or as a homogeneous catalyst, ruthenium binap as gas liquid system. I'm going to talk then about biotransformation using oxygen together with the water in which the enzymes dissolved. Then a 2-phase system using bleach and toluene to do an N-chlorination. Then a crystallization, or 2 different types of crystallization. And lastly, a more complex example, which is an extraction, a liquid-liquid extraction. So to start with then, the undergraduate experiment that we've run for several years now, and is actually published in this paper if you want to get more details from it, involves the selective reaction of a diamine, a difunctional substrate, with acetic anhydride, and the diamines dissolved in toluene, in water, sorry, and the acetic anhydride is dissolved in toluene. And when the two are mixed together, you get a 2-phase system. And then the better the mixing is, the better the rates of reaction. But then there's a few more complicating factors here, that when the reaction to form the monoacetylated product occurs, the side product is acetic acid, and acetic acid can then protonate either the starting material or the monoacetylated product, and then change its phase behavior, so it goes from the organic into the aqueous phase. If there's overreaction, it can diacetylate the product, or if there's underreaction, you get starting material that remains underreacted. So there's quite a lot of physicochemical principles that are introduced in this, and we get the students to start with a batch reaction and generate the data there. So you can see in these tables, they're getting 63% conversion and only 54% selectivity for the monoacetylated product. And then we get them to test a tubular reactor, so the 2 syringe pumps, a T-mixer, and then just try to do the mixing within the tube. And they get a slightly better conversion, slightly better selectivity, but it's still not as good as we get in the fReactors. So then they get the fReactors where there's active mixing this time, and this time the conversion's higher, and the selectivity for the monoacetylated products much longer as well. And what the students can do, they can change the variables, so they can change the residence time, they can change the ratio of the acetic anhydride or the diamine, they can change the temperature, they can change the pH, the solvents, and so you can imagine there's lots of variables which they can test and see what the effect on the selectivity in the reaction is. So it's a really good example to be able to introduce, you know, all the things it can do. And one thing that amazes them is how many experiments they can do in a day. So when they reach steady state, after, as Nick said, 2 or 3 reactor volumes, so maybe 10 mils in this reactor here, they collect maybe 2 more reactor volumes, and then we can analyze the product by NMR, and then they can see very quickly the change in the variables and what effect that has on the selectivity in the reaction. So it's been a really successful experiment, and the details, as I say, are described in well, this J Flowchem paper, but also in the OPRD paper here. A second example is a gas liquid solid system. So this is a typical reaction where we want to hydrogenate nitrobenzene, so not a very interesting substrate, but nevertheless, you know, a typical reaction. So the way in which we do this is by slurrying up the palladium carbon in the methanol solvent here, and that's in a syringe, and we have a flea introduced inside the syringe with a hot plate underneath it that maintains the palladium carbon in slurry. And then as we pump the palladium carbon into the reactor, it maintains it in slurry. And then we inject through syringes hydrogen at multiple points through the reactor. So in that way, we can use the continuous flow system here by injecting hydrogen all the way through. And then as it flows through, then the product comes out. And we can use a back pressure regulator to generate pressure within the system. So in this case, it was 9 bar pressure. We ran it at 25 degrees C, and we had a residence time of 10 minutes. But how did we know to use those conditions? Well, what we did first of all was to actually run the reactions in batch. So we had 5 separate batch reactions, each with the palladium carbon slurried inside them. And then we pressurized them, but ran them for different times. So in reactor 1, we ran it for 5 minutes, reactor 2, 10 minutes, reactor 3, 15 minutes. And then all we did was take it off, open up the reactors, and then analyze the conversion with time. And so that gave us a kinetic profile that allowed us to determine what was the starting point for the residence time in the reactor. So the system was made easier by the ability to just syringe in the hydrogen directly, and it avoids the usual thing of using balloons that people do. And you saw Nick's picture earlier with the balloons on, that's what the balloons were, hydrogen. So transferring the system to continuous flow was very easy to do. And then we could start to develop the system temperatures, ratios. We actually looked at compartmentalization of the palladium carbon in each reactor by putting a little frit in there and stopping the palladium carbon flowing from one reactor to another, using this internal frit to actually maintain it within each reactor and flowing the liquid across. So a gas liquid system we tested was this one here with a dihydro amino acid using ruthenium binap as a catalyst. And this is a soluble catalyst this time. And again, we determined the conditions in the batch and then translated this into flow, this time with a residence time of 30 minutes and 9 bar pressure, slightly exceeding the safety limits, but anyway, it's still fine. The safety limit's actually 40 bar pressure, and that's what it's been tested to. So I don't recommend you go to 40 bar, in which case these fittings blew out. But if you keep round 7 bar, 9 bar, you should be absolutely fine. And in this case, we achieved high conversions and good enantiomeric excesses in the reactor. And actually, one way in which we separated the gas from the liquid was by turning a reactor on its side so that the gas could come out vertically and the liquid could drain out but through gravity. So we just used a reactor at the end here, turned on its side with the gas coming out at the top and the liquid draining out through the bottom. The details of that are in this paper here. Okay, another example, this time an aqueous reaction. What we wanted to do is use an enzyme, galactose oxidase, to oxidize an alcohol to an aldehyde. And if you use air, it's a very slow reaction. It takes 24 hours for the reaction to occur. And the reaction's limited by the concentration of oxygen in the solution. So what we identified was if we use hydrogen peroxide and another enzyme, catalase, to decompose the hydrogen peroxide to generate oxygen, the concentration of oxygen in the solution is very high for a short period of time. And that gives the enzyme enough oxygen food to be able to turn over really rapidly before bubbles start forming in the system and the concentration of the oxygen in the solution goes down. So what we did was we fed in the hydrogen peroxide into the fReactor as an aqueous solution, again with a bit of antifoam in there. and then a mixture of these enzymes and a copper salt was added in as well. And the mixing of the system there gave a really fast reaction and good conversion, and we determined we needed around about 4 fReactors, and with a residence time of around 8 minutes or 10 minutes, we were able to get full conversion and to the aldehyde with no over-oxidation there. So you can see this is an old style of the reactors that were actually in parallel on this hot plate stirrer, and you can see the design's been modified since then. HPLC pumps pumping through the hydrogen peroxide at each of the points here. But actually what we found was that there wasn't enough injection of the hydrogen peroxide, and from this we designed another reactor which has got more injection points of the hydrogen peroxide. So this is a well of hydrogen peroxide with feeds in at each point there. And then as the main channel here, the reaction goes along, the hydrogen peroxide gets injected in. And you can see lots of different examples here of where we tested the reaction. The details, if anybody wants more, are in this paper here, in the Angevanta paper. Another example, a 2-phase system this time, was making chlorine. So we had an amine dissolved in toluene, sodium hypochlorite or bleach in an aqueous phase, and using the fReactor to mix those really quickly, we were able to generate the chloramine in high yield. But chloramines are not very stable, not really nice to handle. And actually what we wanted was the imine. So we injected sodium hydroxide as quite a concentrate solution, again with a phase transfer catalyst, and that gave us a basic solution that then caused the elimination of HCl to generate the imine in high yield. And you can see in this table here, we determined 9 fReactors with a volume of 15 mils and a residence time of about 5 minutes, compared with batch about 20 minutes. Gave us good conversion and good productivity as well, and another different substrate here, again with good conversion. But we also pushed the system by imines themselves are not that stable, so we wanted the amine. So we then took the imine and then did another reaction using the fReactors with an asymmetric transfer hydrogenation catalyst to reduce the imine down to an amine with good selectivity. So this is 3 reactions that were telescoped or integrated, one reaction after another. Okay, this time the residence times were much longer, so it took about 120 minutes in batch and about 30 minutes in the flow reactor. And this is one of the things about the flow reactor, about the fReactors, is that the flow rate can be very slow, and it means it can give you very long residence times. Okay, and this is borne out in this example here about crystallization. So in this case, the crystallizations were quite slow, and we needed residence times of about an hour to do that. So in this case, we injected an acid and an amine, and when those two met in the solution in ethyl acetate methanol, they crystallized out in the reactor, and then they formed a slurry which would slowly flow through and then generate crystals of the diastereomeric product here. And you can see the vials of the crystals collected are in the graph. This is the cumulative yield and the diastereomeric excess as it's formed there. So eventually it did block, but we ran it for 13 reactor volumes, 13 hours here. Eventually it blocked and it was washed out, but by then we've got the data that we needed. Another example, instead of a reactive crystallization, was a cooling crystallization. So here we had a hot solution of succinic acid, and then we pumped the hot solution through lagged pipes into the reactor, and as it cooled down through the pipes, it crystallized out in the reactor here and was able to pump through, and then we used a separation system to be able to separate the solid away from the mother liquors. And one thing that we did here was we wanted to avoid grinding of the crystals, so we modified the stirrer with a little paper clip here that was drilled through the stirrer, and that meant that it would act as a paddle wheel and prevented the grinding that you can get of the crystals in the reactor there, and that's unpublished data. Again, eventually it blocked after about 10 reactor volumes, but by then we had the data that we needed. This is a last example, which is a little bit more complicated, so I'm just going to go through it. The details are in this paper here, but this is a liquid-liquid extraction where we had a mixture of two amines, a product amine and an impurity amine, and then by putting acid in there, we can extract one amine selectively from the organic into the aqueous phase. So what we did was we used an automated optimization system that uses the extraction data by measuring the concentrations by an online HPLC, and then using the computer to change the pump rates, can vary the acid concentration going in, and then automatically work out what is the best amount of acid to extract the most of the amine product without the impurity in there. So this is a diagram showing you the pH at the inlet, the aqueous organic ratio, and the difference in the amine concentration. So the most selective amine was extracted here in the top here, where we got the best selectivity, and that was with this acid concentration here. So we're not using a pH meter, we're just using the HPLC to measure the concentrations of each of the ratios. And we took that a step further by actually doing a reaction and then separating the products in the reaction to try and give us an optimum separation, which is seen in this diagram here. And again, the optimum is over here, where we select an optimum amount of product without the impurities in there. So this is a liquid-liquid extraction using the fReactors for an automated separation. Okay, so hopefully what you've seen from those examples are that the CSTRs, the fReactors used in Cascade, can carry out a range of different multi-phase flow. I've shown you a whole range of different combinations of gas, liquid, solid reactions. They enable testings of reactions at lab scale to determine whether larger scale is viable. I would say they make a really useful alternative to a round bottom flask, and they're intuitive to use, as Nick was saying. And I think overall what it helps you to do is to match the reactor to the chemistry rather than the chemistry to the reactor. So because of the versatility, it's much easier to use them for a variety of different types of reactions. Okay, so it just remains for me to thank the companies that have worked with us, and particularly Asynt, who've been great in working with this, and I'm sure they'd be happy to give you the details of, you know, where to get the reactors from and how to order them and so on. Thank the MIB in Manchester for the biotransformation, and thank you very much for listening.
Thank you, Nick and John. So I'm going to hand over to Mike, who's going to field some questions for you.
Yeah, thanks Nick and John for a great presentation, as always. Lots of good questions in the comments. So I'll just run through them now, fire some off over to you. And the first question we had, so just regarding the pumps that you can use, obviously you stated that you can use HPLC pumps, syringe pumps, gear pumps, etc. Is there a, you know, is one pump better than the other, or if people are beginning, should they focus on syringe pumps or?
Yeah, so I mean, we run all sorts of pumps in our labs, really. And there are advantages and disadvantages of all of them. HPLC pumps are quite good because you have one pump and it will run over a range of flow rates from small to high. Whereas with a syringe pump, you have to change the syringes to try and match your flow rate a little bit to the kind of mechanical movement of the syringe. And HPLC pumps obviously all have, you know, you can essentially have an infinite reservoir on the upstream side, whereas the syringe pump will run out. So there are kind of advantages and disadvantages of both of them. But I think often it's what you might have available in the lab, really. I think one of the things we wanted to do is to try and get people doing flow chemistry easily and quickly. So if you've got HPLC pumps in the lab, then run with HPLC pumps, you don't need to go out and buy additional syringe pumps.
Very good, thank you. And the next one was regarding the slurries, so the palladium carbon hydrogen. Have you found there to be a limitation with regard to the concentration of the slurry before it becomes unusable?
So maybe I can answer that. Yeah, definitely. So if you go to concentrate, you can start getting buildup around there. So we had to vary the amount of palladium carbon a little bit, and that's described in the paper. And also, if we put an internal frit in there, if you put too much palladium carbon, it blocks the frit and prevents it from moving through. Palladium carbon's a very fine solid, and so it's easy to keep it slurried. If you go to different slurries, so rainy nickel, for example, is much more dense, that would be really difficult to flow through. And so it does depend on the type of solid. If your solid's sticky, or you know, the characteristics of your solid are going to actually dictate the way it flows through. But it's a test it and see, try it and see, and alter it, you know, as you go through. So nobody's saying that it's not going to block. Nobody's saying it's going to work for everything. But it works for, you know, things as you've seen in the examples I've shown you. So it's worthwhile testing.
Sounds good. Sounds good. Next one we've got. So when running at high pressure, obviously you've talked about the pressure relief systems and the back pressure valves. I know, but so it's just as simple as getting a little additional extra that you screw into the fReactor, and that will allow you to control the pressure safely. Is it easy to remove pressure from the system at the end if something's at 9 bars?
I mean, Nick can comment on it as well, but we have a range of different back pressure regulators with different, you know, pressure ratings. So the simplest is not having a back pressure regulator at all. So if you're using syringe pumps, for example, you may not need a back pressure regulator. If you're using HPLC pumps, it's very common to have that. If you're doing gases in there, it's very common to use a back pressure regulator to smooth the flow. And so having you know, you can vary the different types. There's different types of back pressure regulators as well. So you can spend quite a lot of money on complicated ones, or you can spend, you know, less money on very simple spring-loaded ones.
Yeah, and from a safety perspective, I think, you know, syringe pumps will tend to stall, and you can set a stall limit on them. So that's a way of regulating the force and consequently the pressure. And HPLC pumps as well often will have a pressure sensor built in. So again, you can regulate using that. So I think you've just got to assess the system that you're working with, really, and identify what, you know, the particular risks are.
Thank you. Next one is regarding the delta between the base of the fReactor and the peak modules. Have you done any work to find out what that delta T is?
Yeah, absolutely. So on the fReactor website, there's, I think under operation of it, there's a graph actually that allows you to see the difference between the temperature of the base temperature and the fluid temperature. So I've just got it up actually for me. So typically a base temperature of 80 degrees C will give you a fluid temperature of about 70 degrees C. Obviously depends where you are in that thing. So there's about a 10 degree.
So just adding to that, you can put a thermocouple inside the reactor and obviously turn up the hot plate so that you get to the temperature within the reactor that you want. And the standard design is peak, which is not very good for heat transfer, but Asynt have done Hastelloy and the steel versions as well if you want better heat transfer. We've actually done thermal imaging on them, so the heat distribution across the plate is reasonably even. But I think, you know, it's just again playing around to get the heat transfer that you want. Depends on the system that you're doing.
Yeah, and I think, you know, if you've got a big flow rate through your system, then obviously the fluid might come in cold and take some time to warm up. Whereas if you've actually got, you know, a smallish flow rate, you know, milliliters per minute or less, then actually the fluid comes in and the base is already at that temperature, so you don't see such a big temperature differential. So again, it's just, I think a lot of this is just about trying to think about the physics of your system and, you know, what's going to affect that. But generally, we run very comfortably just by setting a hot plate temperature, and we do have thermocouples, and we will monitor it maybe once or twice, at the start to build that understanding. So.
Thank you. Next one. Have you ever, do you experience leakages in the system? Now it's being pressure tested, so I would say no.
I mean, look, any system like this has got, 4 pipes on. The lid actually is really good. So we find that, that thumb tightness is really good. And I don't think we ever see leakages there. You've got to make sure your O-ring material is compatible with your solvents. And these are standard HPLC, the low pressure version of HPLC fittings. And actually, a finger tight nip on these is really robust actually. So we have seen, so for example, we were running one reaction where it was really important. We didn't have any leakages, and what we would typically do is put a back pressure regulator in there just at the start of the reaction, fill the reactor, and if there was any leakages at 10 bar, you would see those. You'd maybe see a drop of fluid appear. But after that, you'd kind of confirmed that you didn't have any leakages, we'd take the back pressure regulator off and then just run under atmospheric pressure. And that was a really quick way of checking that we didn't have any leakages in that system.
Okay. I mean, just to add to that, one way we did it as well, that you saw on Nick's example, the use of that pressure monitor. So in some of them, you can actually put a pressure monitor on there, and you can actually determine whether there's a pressure fall across it. I mean, we did pressurize the reactors quite a lot, and over a long period of time, you see a very slow leakage of hydrogen, for example. But as long as you get those fittings right, then they hold the pressure really well.
Very good. Lots of questions about scaling up, kind of process scale. How big can we go with the fReactor?
So there's 2 sizes that we offer on one common base plate at the moment. So there's the kind of the size I've sort of shown, which I think has the internal volumes of, let me just get this right, 1.8 milliliters per stage. So, about 9 milliliters. And then there's the next size up where each stage has a volume of 7.5 milliliters. So about 40 milliliters in total. So it's about a 4 times bigger volume. And, so that's something that Asynt self, and you can scale up that way. We haven't kind of gone beyond that because I think the purpose of this is to put flow chemistry onto a chemist's bench. It's not necessarily about building, a pilot scale facility. But then that's, within the IPRD, for instance, we have, much larger scale 25 litre and 50 litre vessels. But I guess that's another step up. Now, the data you get from this scale, though, we think is really helpful to understand, what you could ultimately achieve at larger scales. It's probably the upper end, so the mixing is really good within these systems, and as you scale up, it probably won't be as good. But maybe you could turn the speed of the mixing down on this system so that you can maybe mimic what you would see in pilot scale. But
yeah, and just to add to that, I mean, obviously the data that you get is good to be able to allow you to scale up. That's one of the reasons why we wanted to develop these reactors in the first place. And we have measured things like mass transfer coefficients, KLAs, and so on. And once you've got the KLA, then that's good information to allow you to go to another reactor, a larger scale. And obviously, large scale reactors, with overhead stirrers, if you've got the right information, you can translate it to the right data, you can translate it into those reactors as well. So, scale up's definitely doable. Yeah, I think that's probably as much as I can say on that at the moment.
Yeah, thank you. One more about, so the new pH probe lid accessory that's come out. I think, was it 25 mil probes as standard it would fit?
12 millimeters diameter, yeah, Mike.
Yeah, someone's just asked if something like that could be used for like an ultrasonic tip probe. So,
yeah, absolutely. I don't see why not. Absolutely. So that's a standard 12 millimeter sized probe fits through our systems. But absolutely, if you can fit your probe through there, go for it.
Yeah, it might
I mean,
be
the
good
other way
way
to do
keeping your solid
ultrasonics
moving.
is to pop everything in an ultrasonic bath as well. So because the reactors are liquid tight, you could put the whole lot in a bath if you wanted. I don't know how you'd arrange that with your stir hot plate.
We have actually done that, and it does help keep your solids moving on some systems. Yeah.
Oh, very good. And one more question that I got was regarding the liquid-liquid, the amine separation. What algorithm do you use for the auto optimization?
Oh, that's a question. I have a feeling that was probably done on SnobFit, but there's a whole group of leads that look at algorithms and look at algorithms for discrete variable optimization and continuous variable optimization. So whoever has asked that question, if they want to get in touch, I'll put you in contact with the right people who can answer that.
Perfect. Sounds good. There's a lot of questions in that we got today. Just looking through the ones that I don't think that we've been through. Is there a lowest flow rate that you'd recommend? I know you've got the calculator on the website.
So yes, it comes down to practicality a little bit.
Does. It's determined by the pumps, you know, by and large. I think the lowest flow rate that we've been to is about 0.01 mils a minute, but I mean that's really slow, and you know it's pushing the limits of, you know, pumps. Yeah,
and then typically you've got to wait a few, you know, 2 or 3 residence times for it to reach steady state, so it could take quite a long time for steady state to be reached. I guess what you might have is you might have a faster phase of one material and then have a smaller dose addition to that material, and I think, you know, so you might have a sort of a higher milliliters per minute in total, but some small additions, and then it comes down to the pumps that you're using, I think.
And the other way of doing it is to add more reactors to it. So what we've done, instead of using 5 reactors, I think the most we've used is 19 reactors, which looks quite impressive, you know, when you see it. But basically, it's just to give a longer residence time, you know, and you just string 19 reactors together.
Asynt are happy to sell 19 reactor-sized kits if anyone wants them. I think that covers most of the questions in the chat. So thank you very much for answering all of those. I will pass back over to Martin now, I think, for some final words.
Thank you. Well, thank you everybody who's attended today. I hope you've all found that very interesting, and you've got some useful knowledge to make decisions on maybe starting out in flow chemistry, or even if you're already in flow chemistry, maybe the reactor could be for you. But any questions we have missed, any questions you'd like to ask, please drop my colleagues at Asynt a line at inquiries@asynt.com. If it doesn't matter how big or small the question is, we're really happy to help you. I know there's a lot of people are really interested in this area, and really want to make sure that they make the right decisions in purchasing such devices. Also, I'd like to mention the Photochemistry Modules. That Nick showed, we are currently working on production design, so it's going to be a little while yet. But we know they work extremely well, and it's just going from those prototypes the university's been working with to making a safe and friendly product for any chemist to utilize on their reactor for photochemistry. And of course, don't forget, please, if you want to find out more about working together with Nick and John, University of Leeds, drop them a line directly. I'm sure we'll be very happy to talk to you. But thank you everybody for attending today, and hopefully we can arrange another fReactor meeting at a later date. Some more information. Let us know what you'd like. So bye bye, and thank you so much again once again to Nick and John.
Thanks very much, everyone.
Thank you. Bye-bye.
Thanks,
Thank you.
everyone.
Take
Thanks,
care.
Nick. Thanks, John.
Bye-bye. Thanks, guys.